Okay, so welcome to the Oxford Discrete Maths and Probability seminar. This week we have a special morning where we have two speakers from Australia, so it's really around the world today. As usual, everyone's muted, but you can ask questions in the chat and we'll unmute people at the end if they want to ask questions. I should remind everyone that, as usual, the talks are recorded, and as long as the speakers agree, we put them on YouTube. Also, for this talk, the slides are up on the web page too, so if there's any problem with links to Australia, at least you can see the slides or follow along in parallel. Okay, so it's a great pleasure to have our first speaker today, Katherine Greenhill. She's going to talk on the small subgraph conditioning method and hypergraphs.
Thank you, Alex. I'd like to thank Alex and Christina for inviting me to talk here today. In a parallel universe where we didn't have the pandemic, I was actually in Oxford for the last 2 weeks, and I would have just got back on the weekend. I would have been visiting Leslie Goldberg, so I'm particularly pleased to be talking here today. And I'm going to talk a bit about the small subgraph conditioning method and particularly applications to hypergraphs. I just want to see, oh, it does work, good. So just a quick overview of this, what the method is. You want to analyze a random variable, and it's a kind of analysis of variance technique that was introduced by Bob Robinson and Nick Wormald in 1992. And you use it when the second moment method does not apply. So if you're lucky, then the small subgraph conditioning will apply. So you want to prove that a particular random variable has probability which tends to 1. You also get more out of this method for free. You get the asymptotic distribution of the random variable and a property called contiguity of 2 probability spaces that I'll tell you about. Now, there's 2 really excellent sources for this method, Nick Wormald's 1999 survey of regular graphs and Janssen's 1995 paper. The title has the word contiguity in it. Okay, so I'm going to talk in general. So let Gn be a sequence of probability. Well, Gn is a probability space. It's indexed by n. You can think of, you know, some sort of random graph model if you like, but this is just abstract. And y is a random variable defined on Gn. So it's really yn, but I'll just say y. And we want to show that the probability that y is positive tends to 1. If you're lucky, the second moment method gives this to you. This is very, very standard. If the second moment is asymptotically equal to the square of the first moment, then you just use Chebyshev's inequality to get what you want. The probability that your random variable is 0 is at least saying that the random variable is as far away from its expectation as the expectation. And so you plug that in. Your upper bound is the variance divided by the expected value of y squared, which just subtracts away the 1 and leaves you with a vanishing little o1. So you see that y is positive with probability which tends to 1. The second moment method works in this case. Okay, but what if this ratio, the second moment to the square of the first moment, tends to some constant c, which is strictly bigger than 1? Then you're not going to get the probability that y is positive tends to 1. The second moment method is not strong enough for what we want to prove. And this is the problem that Robinson and Wormald faced in the 80s when they were studying Hamilton cycles in random 3 regular graphs. So here is a 3 regular graph. And of course, a Hamilton cycle is a cycle that visits all the vertices. So I've shown a Hamilton cycle around the outside. And in a 3 regular graph, if you take a Hamilton cycle away, what you're left with is a perfect matching, as in this picture. So let's introduce some notation. Square brackets n is just the set 1 up to n, and G and D is a uniformly random D regular graph on this vertex set. And for me, in this talk, D is always just a fixed constant, D at least 3. Okay, in 1984, Robinson and Wormald were looking at the number of Hamilton cycles in random cubic graphs, Gn3. And they showed that the ratio of the second moment to the square of the first moment tends to 3 over e, which is bigger than 1. And this implies straight away that the probability that y is positive is around 0.8, well, it's greater than or equal to some constant around 0.896. Fine. In the same paper, they were able to improve this constant to about 0.985 just by looking at triangle-free random three regular graphs. And so this is still quite a long way off 1 minus little o1, but I guess it got them thinking that small cycles can have a big effect on the random variable. And so I guess they thought about that for a while, and they came up with the big breakthrough result in 1992 that almost all cubic graphs are Hamiltonian. They wrote in their paper something like, this result has been, the truth of this result has been suspected for some time, is established for the first time here. And the method that they used to establish the result is now what we call the small subgraph conditioning method. Okay. They followed up 2 years later with a paper that proved that actually for any d at least 3, G and D is asymptotically almost surely Hamiltonian for fixed D. And in that paper, they used the small subgraph conditioning method. They weren't studying the Hamilton cycles directly. They're actually studying perfect matchings and kind of pulling off a random perfect matching at a time to reduce down to a random cubic graph where they knew they had a Hamilton cycle. And then after these 2 papers, Janssen wrote a paper pointing out some things that were implicit in the original work and stating that the same method actually gives you the asymptotic distribution of the random variable and establishes this property called contiguity. And now I can tell you, in this case, what the 2 models are that end up being contiguous. It would be random 3 uniform graphs on the one hand, uniformly random, the normal one. And on the other hand, 3 regular graphs where each graph, the probability that you see that graph is weighted by the number of Hamilton cycles it contains. So the probability of a particular graph is just y of g, the number of Hamilton cycles in g, divided by the expected value of y. Okay, so what is this contiguity of which we speak? It was introduced by Lacam in 1960. And you need 2 sequences of probability spaces defined on the same underlying set, the same sequence of underlying sets. And you say that the 2 sequences are mutually contiguous if the same events have probability which tend to 1 in both spaces. So the probability of some event tends to 1 in one of these spaces if and only if the same thing is true for the other space. Okay. Sometimes you can talk of a one-way contiguity where you just have one of those implications, but we're mostly interested in the if and only if. And we write A curly brackets B if those 2 sequences are contiguous. And Janssen described this as a kind of a qualitative asymptotic equivalence, because if you know that the probability of some event tends to, let's say, 2/3 in one of these models, you really don't know much at all about the probability in the other space, except that it can't tend to 0 or 1. You don't know what number between 0 and 1 it might be. So it doesn't tell you anything about the particular numbers unless that number is tending to 1 or tending to 0. But for us, working in random graphs or random hypergraphs using monotonicity, the sort of events that we're interested in tend to have probability which tends to either 0 or 1. So this is not too much of a constraint. Okay. Now, I introduced that model where cubic graphs are weighted by the number of Hamilton cycles they contain. So we can restate what Robinson and Wormald proved as saying that these 2 models are contiguous using this notation. And now we can see how that works. Think of the weighted model where every graph has probability proportional to the number of Hamilton cycles it contains. Think of how often you're going to see a non-Hamiltonian graph in that model. You'll never see it because it's weighted with a probability which is proportional to 0. So you just don't see them, which means that in the weighted model, they're Hamiltonian with probability 1. And therefore, by contiguity, the other side must be Hamiltonian with probability which at least tends to 1. So the contiguity implies the result that y is positive with probability tending to 1. Okay. Cool. Now, I'll probably focus more on the distribution side of things, which I'm getting to. But before I leave contiguity, I just want to say that we can rephrase this one more time. So we can say that the uniformly random cubic graph is contiguous to something called a superposition of a uniformly random Hamilton cycle and a uniformly random perfect matching. So how this works is you grab your uniformly random Hamilton cycle on n vertices and you grab a uniformly random perfect matching and you put the edges on top of each other, and in this case you get a repeated edge. And we don't like those, and so we reject and we try again. You get a uniformly random Hamilton cycle, uniformly random perfect matching, and if there's no repeated edge, you keep it. So it's just the sort of multi-set union of these two random objects conditioned on having no repeated edges, and that's what a superposition is. And then something constructed in this way also obviously has a Hamilton cycle with probability 1. Okay, you can think of this as saying Hamilton cycle plus perfect matching equals 3 regular graph, except everything involved is uniformly random. And so you get a sort of contiguity arithmetic, which Nick describes in his survey. And the only thing to remember is that in this arithmetic, everything goes except 1 plus 1 does not equal 2. So if you like, you can think about, while I'm saying the next bit, why 2 uniformly random independent perfect matchings superposition does not give you, it's not the same as a random 2 regular graph. Okay. Right. Well, I think it's time that we go through the small subgraph conditioning method in full, in detail. So this is a statement of the theorem introduced by Robinson and Wormald and sort of enhanced or restated by Janssen. We need some constants. So lambda I should be a positive constant and delta I greater than or equal to -1 for all positive integers I. And this is going to have nothing to do with graphs, really. It's just probability spaces and random variables. So now Gn is just some probability space. Yn is the random variable that you're really interested in. And the xi, or xin, are random variables that you think are somehow kind of controlling the yns. The xi should be non-negative integer valued, and all you really care about for yn is that it has a non-zero expectation. Normally, yn is also a counting variable, so it's non-negative integer valued. Okay, then we need 4 conditions, which I can't fit on the same slide, so we'll just put the easy one on this slide, and then the next ones are on the next page. So you need the xin to be asymptotically independent Poisson random variables. So each xi tends in distribution to a random variable zi, which is Poisson, and the mean of zi is the constant lambda I. And all that convergence happens jointly, okay? So you've got a bunch of asymptotically independent Poisson random variables sitting around. Next, A2. You need to be able to control, well, if you condition on the values of the first m of these random variables xi, you need to, that needs to affect the random variable y in a very predictable way. So the expected value of yn conditioned on these first m of the xi's having particular values divided by the expected value of n needs to tend to this product, which involves and really defines some constants delta I, okay? There's a way of rephrasing this where the thing in the numerator is the expected value of yn multiplied by a bunch of falling factorials of the xi's, and that makes the delta i's a little bit easier to see or to figure out what they are. So that A2 is how the random variable yn interacts with these xi's. And the third thing is that once you have these constants lambda I and delta I, and you sum up lambda I delta I squared, it has to be finite. Okay, fine. Fourthly, this is sort of where the magic happens. The ratio of the second moment to the square of the first moment must tend precisely to the value e to the big sum that we just said was finite. So this limiting value, I kind of think of it as the magic number. And this whole thing somehow seems to be black magic that this could ever work at all, but there is some sort of reasons behind it, which I'll tell you about. So if those 4 things are true, then you can make some conclusions. So the distribution version says that that yn divided by, like, scaled by its expectation tends in distribution to a limiting thing called W, which is, as we see here, it's an infinite product. The Zi, remember, are Poisson random variables with mean lambda I. So that's the limiting distribution, and it's kind of weird. This convergence with the yn and the convergence that you get for the xi hold jointly, which means you can kind of grab y and a few of the xi's and let them all tend off to their limits together. And W is positive, essentially with probability 1, if and only if all of the delta i's are strictly bigger than -1. Because you can see in that product, if a delta I equals 0, then W is going to equal 0. Okay, so this is what the limiting, the asymptotic distribution of yn ends up looking like. Right. A different way to state some conclusions, if you prefer the contiguity idea, this is from Nick's survey paper. The probability that yn is positive tends to e to the minus a sum over all the delta i's, which are -1 of lambda I. So for every factor where a 1 plus delta I would give you 0, you need that power of Zi to be 0, and that happens with probability e to the minus lambda I. So, and you get the contiguity of the original space you started with and a space where you reweight everything according to yn. That happens if all of the constants delta I are strictly bigger than -1. That's actually a simplification of what Nick has in his survey, because really you can put the conditioning into the GN if some of those delta i's are equal to -1. So we can actually handle that as well. Okay, so there's this big theorem, that's what it says. And really what's going on is that you have this random variable, and it's quite well controlled by when you condition on the values of the xi. And so most of the variance comes between the groups where the values of, let's say, x1 up to xm are different. Okay. Right. So that's the statement of the theorem. What's been proved by it? There's a lot of results for regular graphs and some results on regular bipartite graphs, and then a very few results on hypergraphs that I'll talk about later. So I'm going to start just writing SSCM instead of small subgraph conditioning method. There's a bunch of people who've done papers using this method. These ones are the sort of structural ones where you're looking for a substructure with probability that it should exist, a substructure. Okay, I'll just give you a couple of examples. Kim and Wormald proved that a random 4 regular graph asymptotically almost surely decomposes into the edge disjoint union of 2 Hamilton cycles. And if I remember rightly, this was the last piece that they needed for their sort of contiguity arithmetic, so that you could write 4 equals ham plus ham. And Prawat and Wormald proved that almost all 5 regular graphs have a 3-flow using small subgraph conditioning, where you orient the edges in a particular way to get the flow, and orient them randomly. And a whole bunch of other results. Okay. There's another more recent body of work where small subgraph conditioning has been used in a different way to make the study of thresholds in random constraint satisfaction a bit easier. So here are 3 results of that kind. For example, you might want to study random colorings in random graphs. And one way to do that is to choose your random graph and then choose a random coloring of that graph. In this case, a GNP or a graph with M edges. But it's easier for the calculations to first partition the vertices into the color classes that you want. And often it's enough to make sure the color classes have roughly equal size. And then secondly, choose the edges, making sure that the edges that you choose respect the coloring, the sort of color classes that you've laid down. So none of them should be monochromatic. And this second model is called the planted model. So you prove that any any events that's true with probability tending to 1 in the planted model is also true with probability tending to 1 in the standard model. So it's like a one-way contiguity. And having this contiguity makes the burden of proof a lot easier, because your bad events don't need to be sort of exponentially small or particularly small. They just need to have probability little o1. So we have the Baps, Koja-Oglin and Efthimu, random colorings in random graphs. Nick and Amin looked at random K-SAT formulae, and recently this whole industry has been kind of blown out of the water with Koja-Oglin, Kappanopoulos and Muller random constraint satisfaction problems. So that's a kind of different flavour of applications of the small subgraph conditioning method. Okay. Oh yeah, and another one that I saw that I don't think fits into this paradigm is some work on community detection in sparse networks, so showing that different random graph models are contiguous. Okay. But for the rest of the talk, I'll focus on the kind of structural results where you want to prove some substructure is present with probability tending to 1 in either regular graphs or later regular uniform hypergraphs. So firstly, let's talk about regular graphs. Because these are sparse graphs, it's no surprise that we work in the configuration model, and the xi are usually just the number of cycles of length I. That's what we choose to work with. So these are the small subgraphs in the name of the method. And we know that they're asymptotically independent Poisson because Bolobash proved that. So that's good. A1 is true. 1 out of 4. And this method works well if the variance is quite well controlled by the short cycles. So these graphs are very sparse. Locally, they look like trees and all your choices are very uniform, except where you encounter a short cycle. So it sort of makes sense. Well, here is a picture of the configuration model. So we're starting with n cells, and each cell contains d points, and then you pair up those points into dn onto pairs. Okay, you shrink the cells down to vertices, and you'll end up with a d-regular multigraph. You may have some loops and some repeated edges, and the probability for the multigraphs is not uniform. It depends on how many loops and how many repeated edges. But if you condition on no loop, so we've got a loop in the right-hand vertex of this picture, and there's a few pairs of repeated edges that you might be able to see. If you condition on the configuration being simple, which means it creates a simple graph, then every simple graph is equally likely because they all correspond to the same number of configurations. And that's why we work in the configuration model. Furthermore, the probability of being simple, if d is a constant, then this is, tends to a constant, and in particular, it's bounded away from 0. So we can divide by this probability when we do conditioning. Okay. Right. So let's say, still talking generally, that y is your random variable of interest in the configurations, and now y sub g is the corresponding variable for the graphs. So you're really interested in y sub g in your d-regular graphs, but you know that the configuration version is going to be easier to work with. So y just counts the number of choices of sets of parts that map down to the substructure that you're interested in. Okay, and let's assume we've run the whole small subgraph conditioning method. We've proved A1 to A4 all hold for y. We want to see how easy or difficult is it to lift that result back up to graphs, from configurations to graphs. Well, if you're only interested in the probability that y is positive, then it's trivial, because if the probability that y is 0 tends to 0 in configurations, then as an upper bound, you can just divide by the probability that your configuration is simple, and you'll get the probability that the random graph variable is equal to 0. So that also tends to 0. That's just immediate. Lovely. That's why we like the configuration model, I guess. And it's also not difficult to check that if you're interested in contiguity and you know that the uniform configuration model is contiguous with the y-weighted configuration model, then that also lifts to the graph world, because the small subgraph conditioning thing is set up so that you can very easily condition on short cycles having particular values. So you just have to condition on no 1 cycle, no 2 cycle, and now you've got a simple configuration, as we'll see. So those two are easy, okay? What about the distribution? If you're interested in the distribution of this random variable, so we know that y divided by its mean scales tends in distribution to w. What can we do? Well, the first thing to note is that A2 immediately gives you the expected value of y for graphs. So we have this ratio the average value of y in the graphs is the same as the average value for y conditioned on your configuration being simple, because every simple graph corresponds to the same number of simple configurations. So this ratio in the middle there is exactly what A2 talks about, and we know that that tends to this e to the minus lambda 1 delta 1 minus lambda 2 delta 2, and you've got those constants at hand, and you can just calculate that. So if you know the expected value in y, you know the expected value asymptotically, you know the expected value for yg. And this works because a configuration gives a simple graph. That event can be described in terms of short cycle counts. Okay, it's sort of obvious. x1 equals x2 equals 0. I emphasize this because we're going to come back to it with the hypergraphs. Okay, so that allows us, to replace the denominator, the expected value of y, by the expected value of yg. And now we need to see what happens to the numerator. So now I'm going to look at yg scaled by the expected value of y. And we use this joint convergence of basically y, x1 and x2. We condition in the configuration model on x1 equals x2 equals 0, and that lot all tends to w conditioned on z1 equals z2 equals 0. And this we can write down. So you lose the I equal 1 and the I equal 2 factor from the big product, and instead you gain exactly the same green stuff out the front that we had before. Okay, and L is some fancy probability thing that I'm sure you all understand, and Svante writes it this way, so I thought I'd better stick to it this way. But this is the upshot of it is that you can take y divided by its yg divided by its expectation. You can replace the denominator and you get the green factor with a positive sign sort of in the numerator, and now we apply this joint convergence step, and those green stuff that just cancels and goes away. And what you're left with is something that looks very much like w, except it just starts at I equals 3. So the short version is, if you want to go from configurations to graphs, you just chop off the I equal 1 and the I equal 2 factors out of this big product, and it works. Okay, so that's all you really need to remember. All right, what about hypergraphs? So I've been working a bit on small subgraph conditioning methods for hypergraphs. Now I'm going to use R for regularity and S for uniformity, just because that was established in the first paper that applied the small subgraph conditioning method to hypergraphs, and I've just sort of stuck with it. So R and S are still fixed constants, and we have to assume that S divides Rn, so that this is so that we have some hypergraphs of this form. Every vertex is in R edges, and every edge has exactly S vertices, right? And you can have a configuration model for that. So here we have N is 6 cells with 4 points each. So I guess R is 4, and I'm going to say that S is 3. So I want a 3 uniform 4 regular hypergraph, which means I have to take all these points, and instead of making pairs, I'm going to partition the points up into parts, NR on S parts, each of size S. So I'm taking triples. And I haven't drawn all of them because it would just be a big mess. But you can do that, you do that randomly, uniformly at random. And just like in the graph case, you might form a loop, which will become an edge which has a repeated vertex in it, and you might form repeated edges. But your hypergraph is simple if it has no loops and no repeated edges, and that's what we want. So G and RS, they're simple hypergraphs. And we also know, as in the graph case, that the probability that your configuration is simple, which means that it gives you a simple hypergraph, tends to a constant. So it's certainly bounded away from 0. Okay, Cooper, Fries, Malloy and Reed proved that in 1996. Right, so that's the configuration model where we'll be working. The random variables xi are very similar to the graph case, except that I like to work with loose cycles where I can. So xi is going to be the number of loose cycles of length I, if I is at least 2. But for x1, I need to make sure I can rule out every kind of loop. So x1 has to count all 1 cycles. Now, these pictures show you 3 different cycles. We've got a loose 6 cycle on the left. That's a 3 uniform, a 6 cycle in a 3 uniform hypergraph. So you can see the edges overlap as little as possible. And every edge gives you s-1 new vertices as you move around, okay? The 2 things on the right are 1 cycles, so they're loops. The top one is loose because it has s equals 4, but it has 3 distinct vertices, x, y, and z, and one of them is repeated. So it's the minimal number of repeats you can get away with. And you can think of this as an edge that loops back onto itself, like a 1 cycle. But as I said before, I need to get rid of all loops. So I let x1 count all possible 1 cycles, which includes things where there's a vertex of multiplicity 3 or more than 2 vertices, 2 or more vertices of multiplicity bigger than 1. Okay, just anything that can go wrong. So those are the random variables that I choose to work with. Now, the same Cooper-Friese-Malloy-Reid proved for us that A1 holds. So these random variables are asymptotically independent Poisson, and we know their means. They look like this. Now, Cooper et al. Actually worked, they didn't work with loose cycles, but in their proof, they show that if you're counting cycles of length I, then the only cycles that really have the biggest asymptotic the only cycles that give a non-negligible relative asymptotic contribution are the loose ones. So asymptotically counting the loose cycles is the same as counting all of the cycles of a given length. So we can just use this, these lambda I for loose cycles as well. So A1 holds. Again, we're 1/4 of the way there. Good. So in the abstract for this talk, I hinted, it was like clickbait, that something goes wrong in hypergraphs. So what is it that needs a little twist in the hypergraph setting? And it's quite subtle, so subtle that I didn't notice it in an earlier paper until a referee pointed it out. So thank you very much to that referee. The point is that the event, the configuration is simple, cannot be described just by conditioning on short cycles. Because is simple means I don't have any loops, which are 1 cycles, but I don't have any repeated edges. I am allowed to have some 2 cycles, and I shouldn't rule them out. If I rule out all 2 cycles, I'm ruling out too much. So it's not captured by conditioning on x1 equals x2 equals 0, that's going too far. And yet just conditioning on no loops, it doesn't go far enough because you somehow need to rule out the repeated edges. But the probability of having a repeated edge is little o1. So normally you don't see them. And so I think that's why it took me, well, I didn't quite realize that they were something that you really had to be careful with. All of your conditional probabilities are going to be fine. You can condition on having no repeated edges and it doesn't really change anything as far as probabilities go. But you have to be careful with the expected value because convergence in distribution does not imply convergence in expectation. And I think I will never, ever, ever forget this again. So in particular, the small subgraph conditioning method will not give us the ratio between the expected value of y in the hypergraph world and the expected value for the configurations. We'll calculate it for configurations, but later if we want to get the distribution for hypergraphs, we need to bring this ratio in ourselves somehow. So that's the whole twist, basically. All right, so now I'll tell you, as far as I know, these are the only kind of structural results that have been proved using this method in hypergraphs. So Cooper, Friese, Malloy, and Reid are the first. In 1996, they looked at perfect matchings in random, regular, uniform hypergraphs. And they found that there's a kind of a threshold. If your degree is high enough relative to S, your uniformity, then you will have perfect matchings, and if it's too low, you won't, except they express the threshold the other way around, if the uniformity is small enough compared to the degree. So the threshold is on both sides, but I've just written one side down for simplicity. If S, your uniformity is less than sigma R, where R is this expression, then you do have perfect matchings with probability tending to 1, and if S is less than that, then you don't. And if you kind of invert this relationship, the degree that you need is about e to the s minus 1, roughly. Okay, perfect matchings are nice still in hypergraphs because they're still regular. They're still one regular spanning objects. Whereas something like a cycle is no longer too regular because you've got, especially a loose cycle, you've got the connection vertices which have degree 2 and all the vertices in the middle that don't, they have degree 1. So Dan Altman, who was an undergraduate at UNSW and is now in Oxford, myself, Mikhail Isayev, who's at Monash, and Reshma Ramadurai, we looked at loose Hamilton cycles, so the analogue of Robinson and Wormald's initial result using small subgraph conditioning. So we were looking at loose Hamilton cycles in these hypergraphs, and we found a threshold for existence. There's a nice expression that R has to satisfy, but this is the asymptotic, so I just gave you the asymptotics today. So if R is bigger than this, e to the s minus 1 divided by s minus 1 and some corrections, then you have a loose Hamilton cycle with probability tending to 1, and we've got the distribution and everything. And if R is too small, or even equal to R rho of s, which happens once, then you don't have any loose, or probability tending to 0, you have 1. And it's notable maybe that the little os of 1, the terms that I've left out, they're exponentially small with respect to s. So that was that, and very hot off the press, it just went up on archive within the last week. Myself and Misha, again, Mikhail Isayev, and Gary Liang, who was a former honours student at UNSW, we looked at spanning trees just for fun, spanning trees in hypergraphs. So I'll tell you more about our definition of spanning tree in a moment. Obviously, if you've got a 2 uniform hypergraph, which is a graph, you know that with probability tending to 1, the thing is connected and it will have a spanning tree, as long as the degree is at least 3. But if your uniformity is 5 or more, then you have a threshold. So spanning trees don't always exist in 5 uniform hypergraphs, for example. So your degree has to be at least e to the s minus 2 divided by s minus 1 plus some stuff, minus some stuff. So we found, you'll see in a moment, the expression for the threshold. Whereas if s is 2, 3, or 4, then any R will do, except for the obvious exception of 2 regular graphs, because, yeah, they might not be connected. So we built, in doing this, on an earlier paper of myself with a former UNSW undergraduate called Matthew Kwan and David Wind, who was an exchange student from Denmark. We were looking at the graph case, and we got almost all of the details of the small subgraph conditioning, except that final second moment step we could only push through for cubic graphs. So we've got the full distribution for cubic graphs. We found in particular, we found the expected number of spanning trees in GND for any D. And Brendan had done some really old work, Brendan McKay, on this. And this was known up to some unknown constant. And so we basically evaluated the constant in that expected value. And so what we've done in this new work is fill out the graph result for all degrees and also extend to hypergraphs, regular uniform hypergraphs. Okay, so good. What do I mean when I say a tree in a hypergraph? There are choices in how you define trees, and this is the tree definition that we went with. So a tree, you want it to be connected and acyclic, but you have to kind of specify how you're defining those terms. And for those of you who know what these are, we were using Burge cycles and Burge paths. So that's kind of allowing things to be connected. As long as you can walk from vertex to vertex to edge, that means those 2 vertices are connected. So I think it's the most natural definition of connectivity. And acyclic, you kind of rule out anything that you could think would possibly cause a cycle. You don't just rule out loose cycles, but really anything that seems reasonable to be defined as a cycle. I don't want to specify exactly what the definition is. In particular, ruling out all 2 cycles means that any 2 edges in the tree can only overlap in 1 vertex. So it's like a loose tree is what you end up with. In particular, this is a linear substructure. And that, in a way, makes them kind of rigid. So there's a necessary condition for a divisibility condition on the number of vertices. You need n-1 to be divisible by s-1, because that's going to be the number of edges in the spanning tree. And we denote this integer by t, okay? So in all of the asymptotics, you just restrict n to satisfy these necessary divisibility conditions. Right, some stuff about trees. So for this definition of tree, n has the form s-1 times t plus 1. We know the number of S uniform trees on n vertices, and you know, reassuringly, we recover Cayley's formula when S is 2. But what is more useful for us is that we can also write down a formula for the number of trees with a given degree sequence. So firstly, we should define a tree degree sequence to be a sequence of positive integers, n positive integers, and they should sum to S times T, because that's the only thing you're going to see in the degree sequence of a tree with with T edges, each containing S vertices. Okay, so for a tree degree sequence with these properties, we can write down the number of S uniform trees on n vertices with this given degree sequence. There's a factor out the front that just depends on S and n, and then there's a product of 1 over some factorials. And you can see that when S is 2, if you know the formula for the graph case, which is due to Moon in 1970, then you do recover this formula. So this is a formula of Bacher. And you can prove all this stuff probably in many ways, but in particular, there's a hypergraph analog of proof of codes that will give you this sort of thing. So this is a useful formula. Right. So I'm going to show you just some details from the calculations that we did for this most recent work. So the expected number, you want to bed in a tree in a configuration in all possible ways, extend that configuration out to a full configuration, and for an expected value, you need to multiply by the probability that you see that particular configuration. So I'll just put the next line in so we can see what P of Rn is. P of Sn is the number of ways to partition Sn points so that you've got n parts of S points, okay? So that's how you count your overall number of configurations, is the PRN in the denominator. Then the blue stuff out the front combined with the xj minus 1 factorial factors, that's just the number of trees with a particular tree degree sequence, which we're summing over. And then once you've got your tree laid down, for each vertex, you say how many parts is that particular vertex in this tree, and you need to identify which points in the cell correspond to each one of those parts. And so that gives us, in the green, the R falling xj. So just R if it's in one, or R times R minus 1 if it's in 2 different parts, and so on. And that's it. And then that allows you to, you've described a tree in a configuration, and you have to multiply by the P of Rn minus St, the number of ways to fill that configuration out to a full configuration. Fill those parts that you've chosen out to a full configuration. Okay, so by the time you've done all that, you have the expected value of y written down. Then you do some manipulation and you do some summing and you show that it's equal to that second line, okay? You hit it with Stirling's formula and see what you get. So what you get is some green stuff, which is constant, and there's a 1 on n out the front. So I want you to notice the n in the denominator. And then the rest of it is a big exponential factor, kind of in red. So the pink stuff is dominating, is really describing the whole behavior of this expected value. If that pink stuff is less than 1, then the expected value is tending to 0 very fast. Even if it's equal to 1, the expected value tends to 0 because it'll be a constant on n. And when the pink stuff is bigger than 1, then the expected value grows. So we need to study the base of the exponential. We take the logarithm and we prove some facts about this function. So that's where we get our threshold from. If S is 2, 3, or 4, then this is positive everywhere it needs to be positive. If S is 5, then there's some threshold result. So the function L really determines where that threshold is. We just prove there's a unique place where it goes from being negative to positive. Okay. And if you're interested, if you're a 5 uniform hypergraph, then 3 regular graphs don't have spanning trees, but 4 regular 5 uniform hypergraphs do have spanning trees, and 3 regular 5 uniform hypergraphs don't. But if you have edges of size 10, your degree has to be 328, which is somehow I don't know, kind of disappointing. Maybe it just means that our trees are very restrictive in some way. It's sort of interesting seeing how these numbers grow. They were it was e to the s minus 2 divided by s minus 1. Okay. So that's the expected value, but for A2, for the property A2, we need to look at short cycles. And really you have to condition on the values of x1 up to xm, but the key step is to understand how y interacts with a single cycle. So we look at the expected value of y times xj divided by expected value of y, and it tends to this product, which tells us the value of delta j. And so this is our value of delta j, and you have to do the full calculations with more than one cycle. And now we have lambdas and deltas, we can put them into the big sum and see that yes, it is a finite sum. You just have to check all that stuff on the denominator is non-zero. And now we know the purple stuff is precisely what we need for the ratio of the second moment to the square of the first moment. Okay, that's our goal. All right. Now, the second moment, I mean, often the short cycles step isn't too bad. For spanning trees, it was a bit involved, and the second moment even more so. So I'm really not going to show you very much at all about the combinatorics of the second moment. But once you have the combinatorics, you'll end up with a big sum over some domain of a combinatorial expression, which is a product of factorials and binomial coefficients and stuff like that. Then you need to do Laplace summation. So it boils down to showing that a certain function, in our case, 2-variable function, has a unique global maximum exactly where you think it should be. So you get your second moment, you sort of scale everything. It ends up being a little function out the front, which I've put in green, which doesn't really matter too much, times the exponential stuff, which really you need to understand very well. And there's a natural domain for the parameters that were that arose in the problem. This is the function phi. So you will have done some Stirling, and you'll have a lot of factors that look like a to the a. And when you take them into a log, it's a log a. So g of x is x log x, and you get a bunch of these. The inequalities defining the domain of this function basically say that everything you're taking g of has to be greater than or equal to 0. And g of 0 is 0. So you need to show that this thing has a unique maximum in that domain at the point we need it to have, which is precisely here, alpha naught and beta naught. So we know that these values will work if we can show that that's where the maximum is. I think I messed up the statement of this lemma because it should allow r equals 2 for s equals 3 and 4, but you know, you get the idea. We want this to be true anywhere the expected value tends to infinity. And we were able to prove that. So that's some analysis, just calculus, lots of calculus. And it means that A4 holds. So we can apply our small subgraph conditioning method to Y, and we will get the result that we want for configurations. And so the final question is lifting it to hypergraphs. So what about the problem, the big problem that I talked about before? Well, luckily I have a PhD student, Haya Al-Dasari, who's been looking at enumeration problems for hypergraphs, sparse enumeration using the switching method. And so she has a result that allows us to calculate these expected values. And in fact, it doesn't have to be regular, the degrees can grow, the uniformity can also grow a little bit. Certainly it's more than enough for our purposes, and it enabled us to prove that the ratio between the expected value for hypergraphs and the expected value in the configuration model is exactly what we need for this whole thing to work. So you just have to port something in from outside, and asymptotic enumeration is a good way to get what you need. Okay, and it gives us the result, and in this case, all you need to do to get the distribution is cross off the I equals 1, the one factors term. And so that's the distribution with the deltas and the lambdas that I specified before. Okay. Right, so that's spanning trees. A really nice ingredient in the proof that Gary Liang found, which enabled us to go beyond what we'd done in the 2014 paper, was this binomial identity that I'd never seen before, but Gary found it in a book or something, and it just enabled us to get a more tractable expression for the second moment and to go beyond what we were able to do in the old paper. So that was really nice. Usually you'll see some generating functions, especially in the short cycles argument, and as I said, Laplace summation. Now there's a theorem in an old paper of mine that I find very useful for doing this Laplace summation, and so I'm kind of going to close with a bit of an infomercial, because I think if you're doing any Laplace summation, you might also find this is a useful theorem. So it's in a paper by myself, Svante Jansen and Andrzej Rucinski on random lifts. Okay, it's like a tool. So say you want to evaluate a sum of combinatorial stuff over some domain, and what you're summing over can be written as, you have a lattice, which is just an additive subgroup of Rm, and often it's just Z to the number of variables that you've got. You just got some integers. I've written the version of the theorem that has the lattice has full rank, so you can't write one of your variables in terms of the others. But in fact, our paper has another theorem that handles not full rank. Now, a lattice always contains the zero vector, but maybe you need to shift it. Your parameters might not, they might need to be shifted, and in fact that was the case in the spanning tree result. So you can add a little shift ln under the summation there. And you also don't want to be summing over a big infinite lattice, so you want, you've got some inequalities on your parameters which you enforce using a kind of blow up of a compact convex set with non-empty interior. So you multiply you've got K, which is this fixed set in Rm. You multiply it by n, and that defines the cutoff of your summation. Okay, and an is probably going to be a product of factorials and powers. The main thing is you can hit it with Stirling. So if your summand away from the boundary has this form, and if you're close to the boundary, it's just O of 1 times this. So there's some stuff out the front called B, there's some stuff in green that doesn't matter very much, and there's the exponential part. And then again, just as we saw with the spanning trees, you want this phi to have a unique maximum in the interior at x0. So you still have to prove that. And there's some other conditions about things being differentiable twice and stuff, not very difficult conditions. Then our theorem just gives you the answer. So the standard Laplace summation argument where you kind of turn things into Gaussians, it just does it all for you. So the answer involves Bn. You see the 2 pi n to the rank on 2 that you would expect. You see the determinant, well, it's the determinant of the Hessian at x0. So it's already in the denominator. So that power of -1/2 should probably just be a power of 1/2. Sorry about that. It's in the denominator with a power of 1/2. The value of the green function at x0 does matter. The determinant of the lattice is usually fairly easy to take, and if it's just a z4th or whatever, then you just get determinant 1. That's no big deal. And what is very important is the value of phi at the maximum point. And so that's just a tool that I find useful for doing Laplace summation, and that is in fact all I wanted to talk to you about today. So thank you.
Great, thank you very much. I accidentally muted myself. If anyone would like to ask questions, do please signal in the chat. So thank you for a very nice talk. We'll go to applause in a couple of minutes, but actually I had one question maybe to start off. So you're talking about spanning trees. Can you say anything about the analog of Hamilton paths or Hamilton cycles?
Well, we've only looked at loose Hamilton cycles so far. I guess the trouble is that the calculations are quite involved, and so it's good to be able to be rather specific about what the object is. And I was thinking in particular about Hamilton cycles, so that you don't have to be so strict on n and the divisibility conditions. It would be nice to be able to allow edges to overlap a bit more, but I think it would really snarl up the calculations.
Right.
Probably doable, but not, I wouldn't necessarily want to.
Okay, fair enough. Christina, you had a question.
So Is it right to interpret your result with Aldasari as essentially saying that if you take the hypergraph configuration model, then really it's sufficient just to condition on having no loops, and you've essentially, at least asymptotically, got something that's basically looking uniform?
Yeah, I guess yes, so the repeated edges must make an effect, but the effect is so small that it just goes into some sort of relative error. Yeah.
Thank you.
Okay. And Oliver.
Not sure if it's quite a question or comment. Well, actually, one comment first. Just the formula for the number of trees, hypertrees, there's some obscure older reference that Thomas Woodtrack pointed us at. I think Selivanov in 1972.
Oh, how are you spelling that?
Selinov.
Okay, great, thank you. We found a few references, but we're never quite sure that we had the oldest one, so thank you.
But Baylor and I didn't either, and Thomas Woodtrack told us there's this one, which seems to be real.
Thank you.
And also, I was going to ask a question, but I think it doesn't make sense, which is, so when you're doing just in random graphs, so you could try to apply the conditioning method in the configuration model, or you could sort of apply it in the simple graph model.
Yeah.
And it looks, for A1 to A3, they're sort of exactly the same. So the calculations that you have to do in the simple graph model, because their expectations sort of conditioned on no loops and multiple edges. I mean, if you've done it in the configuration model, you've also done it in the simple graph model. I was going to say, can't you just think of it that way? But I guess the problem is you get stuck on the second moment one. That's the one thing where you...
Yeah, I think the second moment would be hairy, and because you need the limit to precisely hit the right number, I guess as long as you've got asymptotics where the leading term is correct, in theory it should be possible, but when the degree is constant, I've always found it easier just to work in the configuration model.
I don't think it's a different way of calculating, just a different way of thinking about it. So you can apply the theorem in the configuration model and then use the joint convergence to transfer it to the simple graph model, or you could try to transfer the conditions from...
Oh, right. And
and for A1 to A3, they sort of just transfer automatically because you have to calculate these expectations conditioned on the various x's. So doing that in the simple graph model is just a special case of doing it in the configuration model, because you just put in x1 equals x2 equals 0. But I think that sort of way of thinking about it is probably not useful, because for the last assumption...
Right, what would that look like? I remember something I was going to say about that now that you've just got me thinking about A4. Something that I wanted to say, what's going on in the weighted version is that the x's are still Poisson. Did I say that? The x's are still asymptotically Poisson in the version where you weight everything by y, and then new mean, instead of lambda j, it's lambda j times 1 plus delta j. So that's something that's in the engine. Yeah, sorry, that just reminded me. Okay, thank you.
Okay, if there are no more immediate questions, first let me say that in another half hour, we have a talk from David Wood, but we'll have a break now so people can chat and get coffee and so forth. But before we do that, let me say thank you to Katherine for a great talk. I'm going to unmute, a really enjoyable talk as well. I'm going to unmute everybody and